Hello everyone. Welcome to Controllers Tech. This is the fourth video in the register programming, and today we will see, how can we use I2C with STM32 using registers. Obviously, I am not going to use any HAL-related code here, and there is a lot of registers to cover, so this video will be a bit longer. Let's start by creating the project in Kyle IDE. Create the project folder, and give some name to the project. Now choose the MCU here. I am only going to add the core and device startup files. Here is our project now. Let's add the main file first. I am going to add a main function and a while loop inside it. Let's add some basic library files. These are basically the clock configuration and the timer configuration files. I have already covered them in the first two videos. Let's include them in Kyle also. Include the header files in the main file. This is it for basic setup. Now, let's write a function to configure the I2C. Before we go any further, let's check the reference manual first. This video will only cover the master mode, so let's check it out. Here are the steps given to configure the I2C in the master mode. We need to set the input clock in the CR2 register. Configure the clock control register. Configure the rise time register. And finally enable the peripheral. Then a start condition must be sent. Then there is slave address transmission, and then the data transmission. We will cover them all one by one. We will start with the configuration part. Here are the steps that need to be followed. I have added some more steps for clock and GPIO configuration also. Let's start by enabling the I2C and GPIO clocks. To do so, let's go to the RCC peripheral clock enable register. Here you see, the I2C1 is the 21st bit. And to enable this clock, we need to write a 1 in the 21st position. Now the GPIO clocks. I am using I2C1, and here are the SDA and SEL pins. They are PB8 and PB9. So, I need to enable the GPIO clock. Which is located in our CCA HB1EN register. So, let's write a 1 to the first bit to enable the GPIO clock. Now we need to configure the pins. Here, first of all, we will select the alternate functions for the pins. This can be done in the mode R register. As you know, I am using pin number 8 and 9, so I need to write in mode 8 and mode 9. And to select alternate function, I need to write a 1 and a 0. Which is basically writing a 2 in the 16th and the 18th position. Next, we need to select the open drain output in the O-type register. Here we will just write a 1, in the 8th and 9th bit, for the pin PB8 and PB9. Next, select the high speed for the pins. Again, we need to write a 3, in the 16th and 18th position. Next, select the pull-up for both the pins. In the PUPDR register, I need to write a 1, again in the 16th and 18th position. And now finally, we will configure the alternate functions. This can be done in the AFR register, but before that, we need to see what values we are going to use. As you can see here, AFRL register is used for pins 0 to 7, and if you are using pins 8 to 15, you need to use AFRH register. As I am using I2C1, I need to select AF4. Let's go back to AFRH register. Here I need to write a 4, to the pins 8 and 9, which is basically the 0th and the 4th bits. Here AFR1 means the AFRH register, and in case of AFR low register, use AFR0. That's all for the pins configuration. Now let's start the I2C part. First of all, we will reset the I2C. This can be useful in reinitializing the peripheral after the error, or any locked state. 15th bit of CR1 register can be used for his purpose. So we will first put the I2C in the reset state, and then take it out of the reset. After the reset state, we need to program the peripheral input clock in the CR2 register. So what is the peripheral input clock here? Let's see the datasheet to understand that. As you can see here, the I2C1 is connected to the APB1, which can run at 45 MHz. And this is the clock setup that I am using right now, as I have shown in my first video. The APB1 clock is running at 45 MHz, and that's my peripheral input clock for the I2C1. Here is the CR2 register, and the first 5 bytes are used for frequency. The maximum value can be 50 MHz, and minimum as 2 MHz. These values are anyway in megahertz, and so I just need to input 45 here. Now the clock control register. Pay attention here, as this will involve some calculations. Here I am going to select the standard mode, so 15th bit will be 0. Duty will also be 0, as I am not using the fast mode. And now the CCR value. In standard mode, we can calculate CCR by either using the T-high formula, or T-low formula. I am going to use T-high here. As you can see, the T-high is equal to the rise time for clock, plus the clock high duration. And these values can be found in the datasheet. So basically, the formula for CCR will become like this. Go to the I2C characteristics in the datasheet, and here you can find all the values for your device. I have the clock rise time of 1000 nanoseconds. And clock high time of 4 microseconds, which is 4000 nanoseconds. Also time for PCLK1 can be found by 1 divided by the clock frequency. And finally, the CCR value is 225. Let's write 225 to the CCR register. Next is the calculation for the T-rise. You can read the details here on the reference manual. But, basically it comes to this formula. And we got the T-rise as 46. Let's update it. Now we need to enable the I2C peripheral. We can do that by setting the bit 0 of the CR1 register. Please note that, this here should be bit 0, not 1. This is all for the configuration. Now let's write a function for I2C start. Here we first set the start bit, and then wait for the SB bit to set. This basically indicates that the start condition is generated. Let's see the registers. Start bit is bit 8 of the CR1 register. So write a 1 to the 8th bit. SB is the bit 0 in the status register 1. And if it is set, it means that the start condition generated. So we will wait for the bit 0 to set in the SR1 register. Now let's write a function for writing the data to the I2C device. The description is given here, but you will better understand it with this figure here. So before writing the data, we must check for this particular event, which says that the TXE bit must be 1, to indicate that the buffer is empty. Then we write the data. And after we are finished writing, we check for event EV8, which says that the TXE and BTF bits must be 1 to indicate the transfer has finished. So we will wait for the TXE bit to set, then send the data, and then wait for BTF bit to set. In the status register 1, bit 2 is the BTF bit, and bit 7 is the TXE bit. Let's first wait for the TXE bit to set. Then load the data into the data register. And wait for byte transfer to finish. Next, another function for sending the slave address. Let's see the steps again. Here, after sending the slave address, the ADDR bit will be set to indicate that the transfer is finished. And then we need to read the SR1 and SR2 registers to clear the ADDR bit. ADDR is the bit 1 in the status register 1. So here are the steps need to be followed. First, send the address into the data register. Now wait for the ADDR bit to set. And then just read the SR1 and SR2 registers to clear the ADDR bit. And finally, a function to stop the I2C. Ninth bit of the CR1 register is the stop bit. And we will write a 1 to the 9th bit, in order to stop the I2C. This is basically all, but I just want to add one more function here. I2C write multi can be used, when we want to write more than 1 byte of data at a time. Here I am passing the size as the parameter, which is the number of bytes we want to write. We need to follow the same steps that we did in the write function, but with little changes of course. Let's take a look at that figure again. As you see here, we can send multiple data bytes, but before sending the next data byte, we must perform the check for event 8. That means we must wait for the TXE bit to set. And after sending the last data byte, we will wait for the BTF bit to set. Here, first check if the TXE bit is set. And before sending data, we need to perform the same check every time. Once the last data byte is sent, wait for the BTF bit to set. That's all for the I2C setup. Now let's see some working. First of all, I will include the sysclock config, and timer config as usual. Include the I2C config also. Before going any forward, let's see what device I have. Here I have is a PCF8574, which is used to drive the LCD displays. You can see the input pins right here. We have clock and data pins for the I2C. If you Google the pinout for this module, you can see how the pins are actually connected. The numbering on the LCD here is exactly the same as it is on the module. So we have the 4th pin connected to P0, 5th to P1, 6th to P2, and then from 11 to 14 are connected to the P4 to P7. So here I cannot control the first 3 pins of this module. 4th pin is P0, P1, P2, and then P4 to P7 also. I have some LEDs here, and I will attach them to this module. Notice here that I have first LED connected to P0, second to P1, then this one is P4, P5, P6 and P7. Now connect the VCC to 5 volts, ground to ground, clock to clock, and data to data. Let's send the start condition first. We need the address of the slave here. Let's check the datasheet of the module. In my case, pin A0, A1, and A2 are high, so the address will be 0x4E. These pins are high by default, and if you have more than one module attached to the same I2C pins, you can ground these pins to change the address accordingly. As you can see the sequence here, we send the start first, then send the address, then send the data, and finally stop. Let's send the address 0x4E. I am going to write 0x01, that means I am setting the pin P0 only. And send the stop. Let's build it. Go to Options, and type in the frequency here. Select the ST link. And check reset and run. Let's flash it. You can see only the first LED is on. So the code is working as expected. Let's try to switch the LED. 0x02 means, only the second LED should be on. As expected, it works. I don't have the LED 3 and 4, so I will turn on the fifth one. For that, I will send 0x1 0. I can turn on all of them by writing 0x FF. Things are working just fine here. Let's try to have some more fun with it. I will put this in the while loop, where I will turn on one LED at a time with a delay of 300 milliseconds. So it's working fine, but there is gap of 2 LEDs, and you can see it. Let's try to modify the code a little. And now, we don't have any gap between the LEDs. You can change delay here, to make it look a bit better. Great, it looks awesome now. This is it for this video. You can download the code from the link in the description. Leave comments in case of any doubt. You can mail me if you have any suggestions. Keep watching, be safe, and have a nice day ahead.